Hi there, and welcome to Lesson 3.1 Continued. So today we're going to continue on with our exponential functions and graphs. So previously we learned about what an exponential function looks like, how it compares and how it's different to an algebraic function. Now we're going to talk about a very common one that's used, and this is the one that has the natural base e, which is known as Euler's number. And this right here, that is pronounced as Euler, so it almost looks like it should be spelled like this, Euler, but this is how it's spelled. So Euler's number E is what we are going to be focusing on today and how that plays into exponential functions. So what is E? E is an irrational number. That means it cannot be expressed as a fraction. It's an ongoing, non-repeating decimal that can't ever be expressed as a fraction. Here's what it looks like. E equals 2.718281828459045, and it keeps going on and on. Mainly when we look at E, we just kind of round it to 2.7 if we are writing it out. The calculator will calculate it as the entire number. So what other irrational number do we know? What is another well-known one? Think about it for a second. Okay, did you come up with it? It's pi. We're used to seeing irrational numbers. Pi is also an irrational number. It cannot be expressed by a fraction. It's 3.14159, and it continues on and on as well. Okay, so now we know what E is. So how are we going to use it with regards to an exponential function? So our natural exponential function is written as f of x equals e to the x. So remember, when we have exponential functions, our exponent right here is our variable x. And for the natural exponential function, e is going to be our base. So let's take a look at what the graph of e to x looks like. It looks very similar to what we saw yesterday. Very similar to an exponential function. And that's because it is, because basically what this graph is saying is that we want the function f of x equals 2.7 ... to the x. And remember, before we graphed 2 to the x. Well, this is very close to 2 to the x. It's 2.7 to the x. So these graphs look very similar. All right, so we've been learning about e. Why is this such an important constant? Why is this irrational number e important to us? Well, the reason is it's used actually a lot in the real world with regards to applications. One of the most common ones is in business, and it's used to compound interest continuously. It's also used in science when you're wanting to find out the rate of decay of something or the half-life, things like that, or bacterial growth. It's used in calculus. It's used in many, many different applications. Today we're going to just focus on a business application though. So we have a deposit of $5,000. It's made into a trust fund that pays 7.5% interest. We want to know how much will be accumulated if the interest is compounded quarterly and continuously after 25 years. So we have two different problems that we're wanting to set up here. We want to find out, and what this means is when the interest is compounded, that means computed. How many times is the interest applied basically to the balance? So when it's compounded quarterly or continuously, and continuously means it's constant. Quarterly, there would be 4 quarters in a year, so that would be 4 times a year, whereas continuously means it is constantly refreshing itself. So we need some equations here. Our first equation is when we have a set number of compounds. So for example here, quarterly. So our n would equal 4. N's usually referred to as your number of compounds. Quarterly, so 4 compounds a year, we're going to use this equation. A equals P times the quantity 1 plus R divided by N raised to the NT. And right here is why it's an exponential function. It's because it's raised to the NT. Okay, there's a lot of variables there. We're going to go over them in just a second. The other one that we have is continuous. So when interest is compounded continuously, we're going to use this equation. commonly known as PERT, P-E to the RT. Okay, so we have all these variables. What are they? A is our balance, our amount. That's the amount that we end up with. P is the initial amount, or our principal. So in this case, we have a deposit of $5,000. That's our initial amount. So on this example, P is going to equal 5,000. R is our interest rate. So we have a trust fund that pays 7.5% interest. But we need to change this from percentage to decimal. So this becomes 0.075. We've converted our 7.5% to a decimal. N is the number of compounds, and this only pertains to this equation right here. So in this case, we're going to look at our quarterly. So we have 4 compounds per year, and we are going to compound that for 25 years, and that's our T. So those are all of our variables. Now it just becomes simple. We just plug this into our equations, but we have to make sure that we set it up correctly. So for the first one, compounded quarterly, we need to use this equation right here. So we get 5,000, because that's our P, times 1 plus our rate, our interest rate, which is 0.075. Remember, we need that as a decimal, not as a percentage. Over N, our number of compounds, that's 4, raised to our N times our T, which is 25. Okay, so I want you to go ahead and plug that into your calculator. See what you get. Pause the video. It's going to take a couple seconds. Okay, hopefully you've plugged that in. You should have gotten $32,042 and 93 cents. We were going to round that. That's pretty good. We started with 5,000. After 25 years of quarterly compounding, we're now at $32,000. That's a great profit. But now we're going to see what the difference is if we were to compound it continuously. Okay, so that means we're going to use this equation right here. So we just plug in our variables again. We get A equals 5,000, because that's our initial amount, P. E, that's our constant. Remember, this is just like pi. Raised to the R, our rate is 0.075 times 25. Okay, so again, plug that into your calculator. See what you get. Pause the video. All right, you should have gotten $32,604.10. So we can see we make almost $600 more if it's compounded continuously. So it's to your benefit to have it compounded more times a year. Okay, so that's the only example that we're going to do today. You're going to get lots of practice of this in class. Hope this made sense and hope you guys enjoyed this. Have a good one. See you soon. Bye-bye.